Hey everyone, welcome back to the Explainer. Today, we're unlocking one of the absolute most essential tools in the Python data science ecosystem. We're going to master the NumPy library, and we'll be explaining the chapter on exactly how to use it to transform raw, messy data into clear, actionable insight. Let's get right to it. You know, Carly Fiorina, the former CEO of Hewlett-Packard, once put it brilliantly. She said, "The goal is to turn data into information and information into insight." But think about it. How do we actually bridge that gap? How do we take thousands of raw, totally disjointed numbers and find the meaningful story hiding inside them? Well, that is exactly where our hero, the NumPy library, steps in. So here's our roadmap for explaining the chapter today. We'll start with the jump from data to insight by looking at standard lists versus NumPy arrays, break down the actual anatomy of an array, cover slicing and operations, load up some real-world data, and finally, we'll put it all to the test with the classic iris case study. Okay, let's dive into section 1, lists versus NumPy arrays. If you code in Python, you already know standard lists are incredibly flexible. They're honestly a lot like a junk drawer in your kitchen. They can hold integers, strings, and floats all at the exact same time, just scattered across your computer's memory. But because of that flexibility, they really aren't built for heavy scientific computing. NumPy arrays, on the other hand, strictly enforce a single data type. This uniformity is absolutely crucial because it unlocks incredibly fast element-wise math operations across entire datasets at once. But the real magic, that lies in how they interact with physical memory. So here is their secret power: contiguous memory allocation. Unlike standard lists that basically scatter data wherever there happens to be room, a NumPy array demands a continuous, uninterrupted block of memory. The space is divided into fixed-size positions, and each position is neatly allocated to a single data item right next to the previous one. Because your processor isn't jumping all over the place trying to find the next number, computations on NumPy arrays are just lightning fast. It's a total game changer. Moving right along to section 2, the anatomy of an array. Let's open up the structural toolkit. Every NumPy array has built-in attributes that describe its structure. It's essentially how an array introduces itself to the computer. First up is ndim, which tells us the number of dimensions or axes. A one-dimensional list has one axis, a two-dimensional table has two. Simple enough, right? Next is shape, which gives us a sequence indicating the exact size of the array for each dimension. Then we have dtype, identifying the specific data type of the elements inside, like your integers or floats. And finally, there's item size. So what does item size actually mean in practice? Well, if you query an array's item size and it spits back the number 4, that means each individual element inside that array takes up exactly 4 bytes of memory. And since we know 8 bits make a byte, 4 bytes means we're looking at 32-bit integers. It's just a highly optimized, extremely precise way of tracking exactly how much memory your data is eating up at scale. All right, section 3, slicing and array operations. This is all about navigating our data. Having our data stored efficiently is fantastic, but we have to actually navigate it, pull out specific pieces of info, and perform actions on it to get any real value. Now, a two-dimensional NumPy array maps perfectly onto something we all intuitively get, a standard table. Take this grid of student marks, for example. The student names, Ramesh, Vadika, Harun, Prasad, are our rows, and the subjects, maths, English, science, are our columns. In NumPy speak, the row axis is axis 0, and the column axis is axis 1. To slice into this table and grab what we want, NumPy uses zero-based indexing. You literally just call the array name, put some brackets, drop in the row index I, a comma, and the column index j. So let's say we want Prasad's score in English. We look for the 4th row and the 2nd column. But remember, we start counting at 0. So row 4 is index 3, and column 2 is index 1. We ask for marks 3, 1, and boom, NumPy instantly hands us 72. Once you get the hang of the axes, 2D slicing is a total breeze. Extracting single data points is cool, but arrays have some serious power moves for manipulation. First off, arithmetic. Add two arrays together, and NumPy does element-wise addition instantly, perfectly pairing up the corresponding elements. No messy loops required. Second, reshaping. You can literally take a flat 1D array of 12 elements and seamlessly snap it into a 3x4 grid without changing the data itself at all. And third, splitting. You can cleanly cleave an array into equal parts along any specified axis. It's the ultimate divide and conquer tool for your datasets. Which brings us to Section 4, Loading Real-World Data. Time to get our hands dirty.
Up until now, we've been living in theoretical, perfect array land. But out in the real world, data is stored in messy external files. So here's your exact procedural pipeline for importing a standard CSV using the gen_from_text function. Step 1, point to your file path. Step 2, if your file has text headers, like column names, tell NumPy to ignore them with skip_header=1. Arrays need uniform data types, and we usually just want to crunch the numbers anyway. Step 3, the real world has missing data. You handle this cleanly right at import by setting filling values -999. That gives known values a distinct numeric tag instantly, so your future calculations don't randomly crash on you.
Once the data is safely imported, this is where we start striking gold using NumPy's built-in descriptive statistics. With beautifully simple commands, you can just append .max to find the highest value, .min for the lowest, .mean for the average, and .std for the standard deviation. By applying these to specific axes, like, say, running a mean across all rows for just one specific column, you transform thousands of raw numbers into a crystal-clear summary of the data's behavior.
And let's put it all together in Section 5, the iris case study.
Take a look at this. This is a sample of the raw, famous iris dataset, packed with precise measurements for different flowers. The columns are sepal length, width, petal width, and a numerical tag for the species. In its raw text file form, it is just a massive, overwhelming block of numbers. But to find the insight here, we use the exact skills we just covered. We load the CSV, skip the text header, slice out the columns we want, and maybe split the array completely based on that species number. Now, what's incredibly satisfying about this is how quickly we get answers. By simply loading the array and calling .mean and .stand across the axis, we instantly distill that massive block of chaotic measurements. Right away, we know the average sepal length across the entire dataset is 5.68, and the standard deviation is 0.76. One quick line of Python code completely replaced hours of tedious manual calculation. That, right there, is the true power and efficiency of NumPy. So we've gone on quite a journey today. We went from understanding the limitations of basic Python lists to mastering the contiguous memory magic of the NumPy array. We've explored how to elegantly slice up multidimensional data, safely ingest messy real-world files, and pull out profound statistical truths with just a few simple commands. You absolutely have the foundational tools now to turn a chaotic sea of raw numbers into clear, actionable insights. So I'll leave you with this final provocative thought. What data will you transform next? Thanks so much for tuning into this explainer, and I'll catch you in the next one.